Hey guys, got a few minutes here before we're gonna get started. Are there any questions? We're gonna wait a few minutes and then we're gonna get started.
For the homework, for number one,
Yep.
A and B differ in that B says to set up or describe the Radon-Nikodym derivative on f of t. I don't know if you can do another example of that in class or maybe just explain it a little bit because I'm having a little difficulty understanding.
So this is in question number...
Homework 9.
Yeah, which one?
Number 1.
Yep. Yeah, so so let me bring up the document camera. So in the first question, you're looking at ST divided by ST0. And in the other question, you're looking at the opposite. And so in the first one, you want this to be a martingale, and in the other one, you want this to be a martingale. So what you could do, I mean, what I propose to do is to compute the dynamics of both of these. This is going to be an Ito's lemma calculation. Can you hear me, Nikita?
Yeah, I can hear you. So then I just have one side question really quickly. In number 2 or part 2, it says on f of t. So that part doesn't matter, right? Because both of them you're technically calculating it on f of t on the sigma algebra.
Well, you need these. So in both questions, you're going to be looking at martingales, change of these Radon-Nikodym derivative processes that are going to have the form. So dci is going to have the form minus c
with
I and then some
theta. Okay.
What was the Radon motion? W. You're going to have this for both of them.
Okay.
But the theta you're going to get is going to be different.
Right.
There's going to be one for, so there should probably be an I on this one too.
Okay.
And so what this C here does is that when you're looking at the Radon-Nikodym derivative between Q, I, and then dP, this is going to be equal to CT I on FT. Right? What this means is if I'm looking at the probability on the Q, on a set A, you get that probability by computing an expectation under P of the indicator for the set A and then CTI. And this is true for any A, and this is where the T comes. This is what it means to be here. This T there, this is what comes over here.
Right. Okay.
Right, so you compute what this here is using E2. So you're going to get something here. This is E2. And you're going to get something here, which is again going to be E2. In the two things whatever you're going to get, this is going to be different in the two questions. Right? So you want it to be martingale. Okay, so that means that whatever you're going to get, and so then you change the measure. So this one here is going to become dWt plus your theta I dt, and the same thing here. So this is a 1, the other one is going to be a 2. And then, of course, you have to make sure that it works. So you're also going to have to, this term you're adding over here should be subtracted over here. And then you're going to make everything that's inside here equal to 0.
Okay, thank you.
Okay. So this, let me work out what the first one is, because this is actually where we're going to start tonight's lecture. Alrighty, so right, so tonight we're finally going to get to price derivatives in this continuous time setting that we've been building up on for quite some time now. Right? So we're going to have our model for the bank and the stock. There will be the bank will have the form. This is the bank, and the stock is going to have the form ST. And let me write it down like it is in the homework. So it's ST mu t dt plus sigma t dwt. We are playing here in a model that has one Brownian motion. Okay, so again, we see this linear structure. We see the linear structure here. We see the linear structure here. We've had these a number of times. This here is the same. We can solve this. This here is an ODE because there's a dt here. So this is a smooth solution. This is an exponential of an integral from 0 to t of RU du. This one here, we've had that one before. This is more complicated because this is not smooth. There's a Brownian motion here. And so we will write this. You can find the solution using Ito's lemma. This will be S0, and then there'll be exponentials again, just like before. There'll be an integral from 0 to t, and then there'll be the mu. And then there'll be the Brownian motion term. And then we have to subtract the Greta gradations. It'll be minus 1/2 here of sigma squared. That will be the solution for the stock. All right, so the first one is the bank. The second one is the stock. Okay, so then the first thing we want to know is no arbitrage. Okay, so to guarantee there's no arbitrage, then you need to find, so to get no arbitrage, to ensure that there is no arb, we're going to find the measure Q equivalent to P such that ST divided by S0 is a martingale. That's what we've been doing in discrete time, so we're going to carry on and do the same thing in continuous time. And so the way that we're going to do that is, well, we first need to know what the measures look like. Okay, and then we need to figure out what is the condition on that measure Q that'll make this thing here a martingale. So first we need the Radon-Nikodym derivative process between Q and P. Okay, so we're going to be looking at these exponential martingales that we have talked about last time. So we're looking at dz. And so this is where we go up and look at the filtration. How many Brownian motions are there? Well, there's one. Okay, so if there's one Brownian motion, there's going to be one market price of risk. That's what we talked about last time. So we will have one market price of risk, this will be my theta, and then we'll have the DWT. And this thing here starts out at 1. Okay, so now the name of the game is going to be to create, to figure out what theta here should be, right? Such that ST over S0 is a martingale. Okay, so how do we test for this? Well, we apply E2. So we use E2 to compute D of ST over ST0. So we use E2 to compute this. What we can see is we are dividing. What we can see is we're dividing here. We're dividing ST by ST0. So you can see the effect it's going to have is to replace mu by mu minus r, right? Because we're dividing here, dividing by an exponential is the same thing with a minus. So what we're going to get here on the right-hand side is going to be exactly like S here, except mu is going to be replaced by RT, mu minus RT, and then plus the volatility sigma. Right, so Nikita, you asked about homework 1, and I'm sure more of you have been wondering about homework 1. When you do this for homework 1, the second question in problem 1, then these are switched, right? So S0 is upstairs and S is downstairs, right? So then you're going to get something different here. So just keep that in mind. This here works for the first part of problem 1. And so now we use Gisanov. This is where the market price of risk comes in. So Gisanov, he says that if I want to get a new Brown in motion, we take the old one, and then we correct it with the market price of risk. I think it was Alice that called it the correction term. This is a great word. So a great phrase, so we can call it the correction term. So now we have that, and I know now that this is a martingale. This is a Brown in motion under that measure Q that has this as its Radon-Nikodym derivative process. I'll replace the W here by this WT, WQ, and the way I do it is I'll replace this part here. This is equal to, well, dWTQ, and then minus my theta T dt. And that will allow me to write everything here as it'll be mu t minus RT, and then I'll have minus sigma t theta t. And then I'll have my sigma d dWTQ. And what I want is, this is the goal, I want to be able to write this as a martingale. That means that it should be no dt, we should only have this second term over here. So I want to write this as ST0, and then sigma, and then dWTQ. So for this to hold, so we need theta t to be something very specific. We need theta t to ensure that this drift here is equal to 0. And so we need theta to be mu t minus RT over sigma t. Right. So if I can solve this equation, right? So we need to be able to solve. We need to be able to solve mu t minus RT equals sigma theta. Right. If I can solve this equation, the model has no arbitrage. So you can see sigma here cannot be 0, right? It just won't work. Any questions on this calculation here? So this is the basic framework. We have our money market account, our bank, and then we have the stock. And so popular models here. So examples. The oldest model we have is the Bachelet model. The oldest model we have is the Bachelet model. The oldest model we have is the Bachelet model, where the ST over ST 0 is the discounted stock. Oh, maybe I should. So the oldest model we have is the Bachelet model. R T is just a constant. And we can even put it equal to 0. Maybe we should just put it equal to 0. In that case, the bank account is just equal to 1. I don't have to discount. And then DST will simply just be a Brownian motion, DWTQ. So it doesn't quite fit into this one because I have this term here, but yeah, so that's the oldest one. This is a normally distributed stock price. The famous one is Black-Scholes. And this is actually originally due to Samuelson in '69. Bachelet, this was in 1900. So you see there's a big gap here. Black-Scholes says RT is a constant. It says that the discounted stock price under this measure Q is going to be ST over ST0 times sigma times DWTQ. That's the Black-Scholes model. So this one here was normally distributed. This one here is going to be log normal. You can see it's going to be log normal because, well, the mu is gone. And so you have sigma, that's a constant, integrated with respect to Brownian motion. This is going to be normal. And then you have an exponential of a normal, you're going to get a log normal. So you have Bachelet, you have Black-Scholes. There are many other specifications of this setting that people care about. The next one is, this is Heston's model. Again, just like in Black-Scholes, you take the interest rate just to be a constant. And then the new thing is, so you have your discounted stock price will be, instead of sigma, there'll be a sigma t here, and then there'll be a dwtq. And now this is a stochastic process, and in Heston's model, d sigma t is the square root process that we talked about a number of times. So like a kappa, maybe an alpha minus sigma t dt plus some volatility, beta root sigma t dwtq, and there's a square root here. So that one is Heston's model. There's another one called Stein and Stein's. It's exactly like the one we have up here. R is a constant. and dst over st0 is, instead of the square root of sigma t, you put sigma t dwtq. But then instead of a square root process, you just have an Ornstein-Uhlenbeck. This is a square root process. Square root process, which we have had a few times in the last few weeks. In Stein's model, sigma is an Ornstein-Uhlenbeck process. So the square root over here is gone, and you just have beta. So this here is an Ornstein-Uhlenbeck. So these are stochastic volatility models because the volatility in the stock is a stochastic process. So here we have the Bachelet, Black-Scholes, Heston, and Stein. They all focus on the equity, all focus on the stock. Models that are more focused on the interest rate. Well, those will be
Professor, I have a quick question. So for those two, the Heston and the Stein's model, there was a d sigma t, but for the Black-Scholes, was there still a d sigma t there, or
no? This is a constant. This is a constant.
Oh, okay. So depend.
This is a constant.
So there's different conditions for each of.
Yeah, this is a in Black-Scholes, the volatility is a constant. And this is what gives you the log normality over here.
Okay. Gotcha.
Yeah, so here, this is not constant. This is a stochastic process itself. But this is an example of a stochastic wall model. The volatility is stochastic. And the same thing is true in Stein. This is also a stochastic wall model. Right, so these models, they are equity models. This is all about equity. And the same thing is true for Black-Scholes. More questions? So the last class, so this is focused on equity, right? Because the interest rate these are constants. If we move into fixed income models, then we'll have the most famous one there will be Vasicek. So this is a fixed income model. So this is a stochastic interest rate model. Right, so now we're talking about fixed income. So in Vasicek's model, the focus there is on the R. So DRT is going to be kappa alpha minus RT dt plus beta dwtq. So now the interest rate becomes an Ornstein-Uhlenbeck process. So if you ever end up on a fixed income disk at some point in your life, this is the model you'll be using. Academics, they prefer a different one, right? Because this here is Gaussian. We talked about the Ornstein-Uhlenbeck process being a Gaussian process. So this is a normally distributed interest rate. And academics, they sometimes prefer to have non-negative interest rates. So the alternative there is this CIR model. And this is again a stochastic interest rate model. And this, so again, this is a fixed income. And so the interest rate here is going to be modeled as exactly the same thing as you have before for the drift, but for the volatility, you put in a square root. So this here is a square root process. So as I said, academics, they prefer this one. I have never met a banker. I have never heard of a student coming back saying that you would use a stochastic interest rate that uses this square root process. I have never heard about that. Every single student that has come back, I've had interactions with, they all use the top one here. VesaCheck is the complete dominant model on Wall Street. So here was a handful of models that fit into this framework that we've been talking about. They're all driven by this Brownian motion WTQ. Any questions or comments so far? So now what we should be doing is to devote a few lectures to each model and go through all the calculations. Right, this is what the textbook does. And of course, we don't have time to do this. So we need to be a bit more selective in what we're going to go through. But nonetheless, these are the standard models that are being taught in courses on continuous time and quantitative finance. Any questions about what we have up on the slide so far? So today, I want to go over some of the problems that we have for the final, and these models and those problems are highly related to what we're seeing on these slides here. Right. So the name of the game is derivative pricing. Derivative pricing, well, what you're given is a payoff function. So you're given a payoff function. That's a function from R to R. Right, and then you're giving at time at the end, you're given a payoff f of st. Right, and you want to replicate, so we want to form the conditional expectation, right? So you know that the wealth, so because st divided by st0 is a martingale, you know that xt, the wealth, divided by the money market account is also a martingale. We did that in discrete time, and of course that property is going to carry over into continuous time, right? Where xt, what is xt? Well, it's the number of shares of the bank account times the bank account price plus the number of shares of stock times the stock price. Right, so again, we'll have that dxt is equal to, and this is where we have the self-financing dynamics. The wealth has the dynamics. So this is again from, this is the analog of what we had in discrete time. The changes in x is equal to the number times the price changes. And so we can see we are in a discounted market. So if I'm looking at d of xt divided by st0, then there won't be any changes here, and I'm just going to get that this is delta t, and then it'll be d of st divided by st0. So what the goal is exactly like in discrete time. You have the terminal payoff, right? And we want to replicate. We want to replicate this terminal payoff. So we seek xt. We seek xt such that when I'm looking at the value it has at time capital T, I'm going to get exactly the same as the payoff. Okay, so now we only use martingale theory, so we're going to discount. If I want this to be true, I can discount by the money market account. And then I can use this here as a martingale. Just as in discrete time, wealth divided by the bank account, this is going to be a martingale. And the reason that it's a martingale is because this is how we constructed the measure Q. So we'll use the martingale property. So the conditional expectation of xt divided by the bank, right, that's the martingale property. This is x little t divided by st0. But of course, if I want that to be true, I plug it in. Plug in what it is. It's st divided by st0 given ft. And so this gives me exactly what the wealth is. I want to have on the right-hand side, this is a martingale. This is a martingale under Q. And this one here, this is the discounted wealth. It has to be equal to this conditional expectation. It's a martingale under Q, so for example, I can write this as an integral with respect to the Brownian motion. So the initial wealth, for example, will just be x0. That's going to be exactly this expectation we're looking at. So we need to be able to compute these conditional expectations. So for example, when RT is a constant, what we'll get here is that xt, the wealth, is going to be given by an expectation under Q, and then you would have f of st times e to the minus rt minus t. So can we compute such things? Well, let's try to do it in a few examples. So we could start by looking at Black-Scholes. So if you look at a Black-Scholes example.
Professor, hold on. Why did when RT is a constant R allow us to make that conclusion? The xt equals.
Well, because
I didn't follow this.
If this is a constant, right, then you're going to get that st0 is equal to e to the rt, right?
Oh, okay. You plugged it in, and then okay, I see.
That's the one we have up here, right? When r is a constant, st0 becomes e to the r times t.
Gotcha. Yeah.
And then you have it over here, right? And you have it over here. You combine these two, and you're going to get this.
I see. Okay.
Because this thing here, this is e to the rt. This thing here, this is e to the r little t. And so I move this thing to the other side, I'm going to get this term here.
Okay. Gotcha.
Makes sense, right?
Yeah.
I'm missing a condition in here. There should be a condition on ft, otherwise it won't work. Other questions? Are there other questions before we start doing some of these examples? So if we do an example, S of t, we've done this one here in the very beginning, but nevertheless, maybe we should do it again. If you want to get, a PDE, say in Black-Scholes, so take R to be constant. As a constant R, and take sigma t as a constant sigma, right? So these two things combined, this is Black-Scholes. So let's put ourselves into the Black-Scholes framework. That means R is a constant and sigma is a constant. So in this case, we go back to the very first slide. In this case, the discounted stock under the risk neutral measure was a martingale with the dynamics up here, and now sigma is a constant, right? So in this case, we'll have that the discounted stock price is equal to a martingale constant volatility, right? That's the constant from up here, dWTQ. So that's the discounted stock price. So if I want to undiscount it, then if this thing here has growth R, then I'll need to add that drift back up, right? When I discounted it to begin with, I moved from mu to mu minus R. That's when I discounted. So now if I want to move back to the undiscounted ones, I'll have to add that R up back in the drift. So I'll get here, this will be ST, then it'll be RT dt, plus that, and R was a constant, so this will be R dt plus sigma dWTQ. So this is also why you see the growth rate. That's the same thing as in discrete time. The expected growth rate of the stock in discrete time was also R. And this is the same thing here. So if I'm interested, and I am interested in computing the conditional expectation of the conditional expectation that we're interested in here is this F discounted. So F discounted, so we want to compute F of ST discounted by the money market account. We want to compute this conditional expectation. And what is it going to be? Well, we're going to make the guess that this is equal to a function of the current value of S. This is when the Markov property comes in. And then time. So what do we know about the function G? Well, we'll know that if I look at it at the end, then the left-hand side becomes, well, it'll be F of ST e to the minus RT. So I want this to be equal to, at the end, I'll get on the right-hand side, G of ST and T. Okay, so I now replace S by X. I'm going to get the terminal condition that says that g of x at the end is going to be exactly f of x e to the minus r capital T. And then I'm interested in what happens before. That's where we apply Ito's lemma, because I know that the left-hand side is a martingale. So I apply Ito's lemma. Apply Ito to compute. So what we have here, dg of st. Apply Ito's lemma, so we need to look for Brownian motion terms. That's inside S. So I'll get here g1 of stt dst. And then because there's Brownian motion inside S, I need two derivatives, so g11 of st and t graduation of S. And then I need the time derivative g2 stt, and then it's going to be dt. And then I can plug in what the dynamics are for S and the graduation. So I need to look at my ds up here. I'll take this long expression, copy it into S's place down here. It'll be g1 of st and t, and then inside here I'll have st r dt plus st sigma dwtq. That was my S. Now two more terms. I need credit gradation. 1/2 g11 of st and t, and then credit gradation of S. I need to look at how does S's dynamics look like. Well, there's drift and volatility as always. When I compute the credit gradation, I don't need to worry about the dt term. I just need to worry about the volatility term. What I need to do is I need to square the integrand. So I need to do S squared here and sigma squared here, and then credit gradation of Brownian motion. That's going to be dt. So I'll get here st squared sigma squared dt. And then there is the last term over here. This is the credit grade. This is the time derivative g2 stt dt. Right, and I know that this is a martingale. It's a Libby martingale. It's a conditional expectation of a random variable. That's a Libby martingale. And so it has no drift. So this is going to be equal to 0 dt, and plus whatever the volatility term will then be, it'll be g1 stt, it'll be st sigma dwtq. So now I get my PD. So we need, right, this was the question mark. I need 0, this 0 here has to be equal to everything up here that sits in front of dt. So I'll get g1 stnt str plus 1/2 g11 stnt st squared sigma squared plus g2 stnt. So we replace st with x to get the PD. 0 is equal to g1 of x xr plus 1/2 g11 xt x squared sigma squared plus g2 of xt. So that's my PDE. I have the terminal condition, and I have the PD. So given that I can solve it, I'll then get that my discounted wealth is going to be this G of ST and T. Equivalently, the replicating portfolio is given as this quantity here. So if I'm interested in the initial wealth that will take me to that terminal payoff, I'll take little t to be 0 here, and this is going to give me the initial value of the replicating portfolio. So if you flip back through your notes, when we started doing continuous time, we had an exercise more or less like this one, where we figured out what the Black-Scholes PD was, and here we have it again.
Wait, is it negative RT? E is a negative RT?
Did I mess up the signs here? Let me just, what was it we had? So G is that conditional expectation here. That's the martingale. So G is here. Copy over. This one here was my G. This was my G of ST and T. That is X over E to the RT. X E to the RT. So now I see what you're saying. There should be a plus there. Move this one over there. Thank you. Other questions? So this was the Black-Scholes PD. I had a few more examples prepared, so let me do a couple more. We have some time to do a few more examples. So the next one, let me share my screen. So so we are in do some of these final problems. I had number 16 in mind. So here's another one. Here's another one. So you have problem number 16 says you take a Brownian motion and let it generate the filtration. So if T, I'm just going to copy some of it on the paper. So the filtration is generated by one Brownian motion. You take a stock that has that form. Question is it arbitrage free? Is it Markov? And then there's in question number 3, there's a question about how do you price a payoff that gives you $1 if the stock price is not too big? How do you construct a replicating portfolio for that claim? Okay, so let's try to answer some of these questions. And then you interrupt me when there's something that is not clear. So we have, this is our F, and the first question is, when I look at DST being more or less the same as what we had here, there will be BT in the drift, and then just the volatility, which is equal to 1. Is it arbitrage free? Well, we go through the motion. There's one Brownian motion in the filtration, so I know that the Radon-Nikodym derivative processes, they all have the form. There's going to be one Brownian motion driving everything. There's going to be exactly one market price at risk. And then Gisanov theorem says that if I know what that one is, I'm going to get a new Brownian motion by taking the old one. And if there's a minus sign here, there's going to be a plus sign here. So that's Gisanov. And then I can replace that dB up here. I solve for dB in this equation, I'll get dBTQ. And then with a minus theta t dt. Right, so these are the P dynamics because this is a P Brownian motion. Now I'm going to write down the Q dynamics. This is ST, and then it'll be BT. And then there'll be a minus of theta. And then I'll have plus dBTQ. Right, so if I want to have no arbitrage, then what? I need to find a theta such that there is no drift here. Okay, so I set theta t just to be bt. That's not so bad. Then I have a martingale. The interest rate in this model here, I think, is taken to be 0. Right. Are we good on the first part here? We've seen this a few times by now. Then the next one is the Markov property. So is S Markov on the P? What about on the Q? And so then you need, this is a little bit more tricky. So we need a good way to determine whether or not we have a Markov process or not. So if I write down on the P, let me write down the dynamics next to each other. So I'll have dst is equal to st bt dt plus dbt. And on the Q, I'll just have st dbtq. So what do we think here? Is S Markov on the P, is S Markov on the Q? Well, on the Q, the answer is yes, because right, so to figure out when and if a stochastic process is Markovian, what you do is you look at the right-hand side and you look at the coefficients. So look at the coefficients. So there's a drift coefficient. Here the drift, this is a function of S and B. And the wall is this is a function of S. So because the drift is a function of both ST and BT, because S's drift is a function of both ST and BT, this here is not Markovian. If you want S to be Markovian, you need more processes. This is not Markov. ST is not Markov, but if I included B here, if I looked at the pair, then this is Markov. We have not discussed a result like this one. We haven't used a result like this one. Over here, the situation is different, because here the drift is a function of ST, right, just 0, and the wall is a function of ST. So ST is Markov. So the way to figure out these Markov processes is to look at what the drift and the volatility is. And this becomes important because, so for example, if I were to look at a function of ST as before and compute the conditional expectation on the P, and I look at it here on the Q, knowing when it's Markov and when it's not Markov, it becomes important when you're looking for conditional expectations of functions of this underlying process. Like in the bottom one, this is going to be a function of ST and T just as before. But the top one, because S by itself is not Markov, you're going to need a function of ST as well as BT as well as T. So then what it means is that if you were to compute the expectation on the P, you need the two-dimensional E2, whereas if you compute the conditional expectation on the Q, you just need the one-dimensional E2. And for pricing purposes, it's this one here we need. This is needed. This is needed to price the payoff F of ST. It's not the top one, it's the bottom one. Right, so the tool that we have here, it says that you should be looking for drift and volatilities and see what your functions are. Whatever the drift and volatility are functions of, this is how many things you need to keep track of when you compute conditional expectations in this form here. Okay, any questions on this one? So we had the first one, we had the second one. What was the third question again? Let's have a look. Third question asks us to figure out what the price is of this payoff. So let me write down the payoff again, so I get it right. We're looking at f of x. This is the indicator when k is bigger than x. Okay. And you've been told that you can express this in terms of the current price, and you can also use this normal distribution function and its derivative, the density, if we so need. All right, so let's try to do that one. Let's try to do that one. Right, so we're interested in calculating the conditional expectation of exactly this function here, 1k bigger than S capital T, given if T, might be interested in figuring out what this function is there on the right hand side. Alrighty, so how do we get started on this one? We have a Black-Scholes model. We have a Black-Scholes model, right? This is how it looks like. I can solve for this here. This here is the same. We had that solution before. This is a linear equation, so it's going to be an exponential. So ST is the initial value, and then an exponential. I get Brownian motion minus 1/2 the quadratic variation, which is T. So that's my S. That's my S. So I can take this solution here and I can feed it. I can feed it into this formula here. So I'm try that. Expectation under Q, indicator K bigger than, and then that solution. S0 e to the BT Q minus 1/2 T. Some of you might recognize how close this is to some of the calculations you've been doing in your homework. And so how do we work out what this conditional expectation here is? So let's see, is Ibrahim here tonight? If Ibrahim is here tonight, I am sure, Ibrahim, you know exactly how to do this because you've suggested this a million times.
Brownian increments?
Yes, it's always the same, right?
Yes.
Always the same. Right, it has worked before, so it's going to work again. Like that is how it goes. So you add and subtract the same thing over here. You're going to get a k bigger than this S0 e to the b q t, and then we have a little t. Now we're going to get independence. So, but I should also add it back up. I need to make the equality sign be true. And then we condition on ft. So comes the time when we use the independence lemma. Take out what's known, condition an average over the rest. So here I compute the unconditional expectation. Maybe I could move S0 on the other side. Then I'll have, maybe I could put log over here too. Put log over there, and then I'll have b tq minus b little tq. And I take this one out because he is measurable with respect to ft, replace him by a dummy. Let's call the dummy for Rutgers. Minus 1/2 t. When we're done computing all this stuff, we replace the dummy Rutgers by btq. Okay, so what's that stuff? We have to compute what we have in here. This is a probability. It's an expectation of an indicator. It's going to become a probability. This is the probability Q of what? Q of a lot of things. So we will have drop the indicator because now it's a probability. So we will move that thing to the other side. I will have BTQ minus B little tq. That thing is small. And then I move all the other stuff to the other side. I'll get log K over S naught plus 1/2 t minus my Rutgers. When I'm done computing, I'll put Rutgers equal to the Brownian motion. So I'm allowed to express everything here in terms of the normal distribution and the normal density. And the random quantity is this one. He's not standard normal, so I need to standardize him. And the way I do that is by dividing by the square root of t minus t. And then this thing over here, square root of t minus t. Now it becomes standard normal. Now it becomes standard normal. So this here becomes n of that mess over here on the right hand side, log K over S naught plus 1/2 t.
Okay, come on back. Come on with me. No.
You got 1/2 t. It's time to put the bt back in there. Time to put the bt back in there. This will be minus btq divided by root t minus t. So that's my wealth. This is my xt. This here is my xt.
Wait, is the n should be the n is standing in for normal distribution function?
Yep. Yep.
Should there be like
that was what was given in the let me go back and share this. This was what was given in the problem. Problem number 16, right? This is the payoff. And then it says you are allowed to use the standard normal distribution function and its derivative.
Oh, okay, standard normal. Gotcha.
Yeah, it's a standard normal. Right.
Right.
That's why we
we
normalized it.
normalized it. Okay. All right, got it.
Questions?
Yeah, I have hold on, let me repen this screen. I just have a question about when it got a little confusing.
What part?
Like when we added and subtracted to create the can you still hear me?
Yep.
We added and subtracted to create the independent increment.
Yep.
We're doing it in like this like indicator function.
Yeah.
And that's okay too, even though it's not like even though it's like is it like in a function, or is it like what part of the function it?
This mess here, right? Just let me write it in red here. Like this mess here, this is some gigantic function of the increment. And the little one, right? It's not a particularly pretty function, but it's just some big function where we can even write out what is f of a comma b. What is going to be this indicator, k bigger than s0, e to the, and then a is what? A up there plus b minus 1/2 t.
Okay. I think I got you. Yeah, I just wasn't seeing it as like a function of the variable, but now I got you.
Okay. No other questions, comments? Are there other questions or comments? So the last step is find the replicating like the investment strategy. And to find the investment strategy, the way that goes is you just compute the dynamics, right? So we're looking for that delta. So I know that dxt, this is going to be, well, it's discounted because the interest rate is 0. This is going to be delta t dst. So this is going to be delta t st sigma d btq, because the risk neutral dynamics of S were exactly like that. So what is delta? Well, thankfully, we know what we have up here. Like xt is equal to this. So I compute d of x. I'm going to have this form. Like x here is a martingale, so there's going to be no drift in all of this, because we computed. This object here is a Levy martingale, so there will be no drift inside this term here. It's just going to be Brownian motion term. So what is delta? Well, we compute d of this top formula here, d of n log k over s0 plus 1/2 t minus btq divided by the square root of t minus t. when this is a function applied to a stochastic process, I know how to compute this. This is equal to n prime. So n
Does
prime.
it end up being just the PDF, or?
Yeah, this is the density, but evaluated at some point, right?
Yeah.
So again, maybe we should write this out because that thing about the function came out before. This xt, what you're seeing up here, this is some gigantic function of btq and t, right? Where g of, say, at, this is defined to be n log k over s naught plus 1/2 t minus a divided by square root t minus t. So if I am to compute the dynamics, I need to compute the derivative g1, I need to compute g1, g11, and g2, right, to use Ito's lemma. But in this particular case, I know that it's a martingale, so I really don't care about these last two terms. I don't care about these last two terms because I know that the dt terms will add up to 0 because this is given to be a martingale. So I don't care about those. I'll just write out the first ones. And I get this n prime of all that mess in there. Log k over s naught plus 1/2 t minus a divided by root t minus t. That was the outer guy. Then I have to multiply by the derivative of what's inside. This is minus, because there's a minus on the a, 1 divided by square root t minus t. So that's what I'm going to get here when I use Ito's lemma. It's going to become a minus here, this n prime log k over s naught plus 1/2 t minus btq, everything divided by what we have here, times 1 over square root t minus t, and then it's dbtq. And what I want it to be is this term. So I want this to be delta t sigma st. So I solve for delta. So solve for delta, it'll be minus n prime log k over s naught 1/2 t minus btq divided by square root t minus t. One over square root t minus t, 1 over sigma st. So if you want to replicate, this is how you have to trade. This is how many shares you have to hold at time little t. Are there any questions on this part?
Yes. So you wrote DXT like halfway through the page.
Yeah.
And then yes, and then you said equals to delta T DST. How come that's equivalent to the one right underneath your finger?
This one.
Yeah.
Because what is DST? Well, on one hand, it was given in the problem that DST was right, DST was equal to, was it ST and then BT dt plus dBT.
Okay.
Or if you want to, this is a p Brownian motion. If you want to write it as a q Brownian motion, it's going to be ST dBT q.
Okay.
And sigma, maybe this is just old habit to put a sigma in there. Sigma is probably equal to 1, huh?
But didn't we have sigma T?
Sigma is equal to 1.
But isn't that the market price of risk?
No. No. The market price of risk is not sigma.
Oh wait, my bad. That's theta.
That's theta, right?
Yes.
That's this one.
Yes.
Right. So this is what was given, right?
Okay, I see it now.
And I put a sigma here. I should not have put my sigma later on, but it's, yeah, that's just old habit. No, the market price of risk is theta. Theta is stochastic.
Okay. Thank you.
Yep. This was old habit. Other questions? So we have 5 minutes left, and instead of going through a new problem, maybe there are some questions about the homework that we should square away before. Are there any issues about the homework that you guys want to talk about?
I have a question about, just want to review a concept. Do you remember when the things we were doing during this lecture where it was like we add the G1, the G11, and the G2?
Yeah.
That was from Ito's.
Yes.
Is that from Ito's? Okay. It's from
Yep.
Ito's lemma that says.
So let me bring it back up here. So when we get the PDE, this part here, G1, G11, and G2.
Mm-hmm.
Yep.
And Ito's lemma shows us how to take, is it related to the dynamics?
Yeah, Ito's lemma will give you the dynamics.
And when we say dynamics, is it similar to taking the, because I see we put like a D in front of the things, but I wasn't exactly sure what that meant formally.
But it means that instead of writing the long way, the D form is just I throw away the integrals. Like if I were to write out the long way for this one, I can do that.
Right.
And it'll be G of ST, T is equal to the initial point plus interval from 0 to T, G1 of SU, U, SU, R, DU plus SU sigma DWU Q plus an interval from 0 to T, 1/2 G11 SU U SU squared sigma squared du plus an interval from 0 to T, G2 of SU U du.
So the D is shorthand for
this.
this.
Yeah. That's all it is.
Oh, okay, I see. And the T is the upper limit.
T is the upper limit, yeah. But if you don't like T up there, you can put anything else. You can put an S here. Then you just put an S here. Like little s, and this is big S, right? You can also put another lower limit here. You can put X.
Okay.
This is just too much to write all the time, and nobody does it.
Right.
All textbooks, people drop these intervals. It's the same thing. When you write in calculus 101, so you want to write the interval from 0 to 1 of, say, sine x dx.
Yeah.
If I were to teach calculus 101, which I'm not, but if I were, we would not be writing this, right? We would just write an integral, and we would just write sine 0 to 1. I mean, how many times do you need to write sine x dx here? Why not just write that? Because it doesn't have any meaning by itself. The only thing that has meaning is that this here is equal to a limit as some partition goes to 0 of Riemann sums. Right, so something like 1 over n, and then sine of some, if it's from 0 to 1, it's going to be something like a k over n, and then you sum from k equals 0 to n minus 1. Like this is what has meaning. This stuff here is just notation.
Right, yeah.
And the same thing is true up here. The stuff that has meaning is this integral, like integral with respect to du, integral with respect to dw. That has meaning and is given as a limit of these approximating Taylor sums. But however I write that, I can write all these integrals. I can forget about these integrals and just write it out in this sloppy notation. Right? It all means, that's just notation. There's no particular meaning behind that. Just as whether I write it like this or write it like that, it's all the same, right? There's a limit here. This is what has meaning.
Gotcha. Yeah, no, I just want to remind myself.
Yeah, that's fine. Just for whatever you do not call this a derivative. Like, this is not a derivative, right? Whatever word you want to slap on it, that's fine. But mathematicians, you get kind of like picky on when you use the word derivative, and the thing that you're differentiating has no derivative. So don't do that. So Steve Shreves, that wrote the book, he likes to call this a differential. I think that's a horrible name, but he sticks to it. Many mathematicians that work in this area, you will call this the dynamics. And so this is what I've stuck with. I don't like the word differential because there is something called differential equations in math, in particular in discrete math. And when you might want to think about this word differential as being linked to this concept, and dynamics seem to be more appropriate here. At least some of us believe that, but that's also just words. Just don't call it a derivative. Like ST here has no derivative because there's a Brownian motion sitting in here, right? There's this term here, there's no derivative there.
So they're all, okay, we all say dynamics or the differential of.
Yeah, if you want to say differential, I'm not going to haunt you with that. I mean, it's up to you. It's also, again, if you understand it, you can call it a derivative. Like, as long as you understand that this is not a derivative in any traditional form that you have seen in other courses. That's not how one can think about this.
Okay. Yeah.
Okay, that pushes up to 8. I have office hours, so yeah, Amima is asking. I have office hours tomorrow morning. Amima, I believe we have office hours tomorrow morning at 9 o'clock. Right.
Yeah, I remember you changed it a couple weeks back.
Yeah, this is 9 o'clock. This is 9 a.m. Okay. Otherwise, have a good night, guys, and I will see you either tomorrow morning or I will see you on Tuesday. All right, take care.
Thank you, sir.
You're welcome.